This is a video on L'Hopital's rule. That's how it's pronounced, L'Hopital's. And it can be spelled with or without that S in the middle anyway, and I usually spell it without, so it doesn't make any difference. But it is used for doing limits where we get an indeterminate form of a certain type. So all of these are what we call indeterminate forms, okay? So you might think that they should be determinate, but remember we're talking about limits. So let's just take an example, 1 to the infinity. Well, we're talking about a limit, so we're approaching 1 as we go to infinity. Well, what if we have approaching from the left and we have 0.999999 going to infinity? The number is going to keep getting smaller as you keep multiplying by itself, versus if you have 1.01 and you're multiplying it, it'll get bigger. So that's just an example of why that would be indeterminate. Infinity minus infinity is an easy one to understand why it's indeterminate. If you think about something like, for example, if we take infinity just means that it goes on forever. It doesn't mean something's bigger, okay? I mean, but they can kind of be bigger, so to speak. But if you take, for example, the whole numbers, which would be 0, 1, 2, 3, 4, 5, 6, 7, 8, etc., and you subtract, that goes to infinity, and you subtract the natural numbers, which is just 1, 2, 3, 4, 5, 6, 7, 8, you subtract those two things, you get 0, the number 0. So you get one thing in that. So versus different infinity minus infinity might be nothing left in it, or it might still be infinity. So like if we take the real numbers and we subtract the whole numbers, you still get infinity, because just because we take out the whole numbers doesn't mean I still don't have infinitely many things left. So fortunately for us, these indeterminate forms over here, we do not have to know how to do the limits. And so because of time, we want to get through everything. We're only going to do how to deal with these two types of indeterminate forms, and we use L'Hopital's rule to solve them. We've been doing those before with other things, but now we're going to do it with L'Hopital's rule if we can, because it makes it a little bit quicker. All right, so L'Hopital's rule says if you have a limit of a quotient, so you have a function over a function, and you take the limit, and you get 0 over 0 or infinity over infinity, then we can replace both f and g by their derivatives, okay? And then take the limit again and see if it's not indeterminate. So basically, so it'll be easier to see examples to understand that. But basically, and when we say infinity over infinity, it's any infinity. So it doesn't have to be positive. They don't have to both be negative. They can be either one. So this is sort of the more official written out. So if you find out that you have this limit you're trying to do, and the limit of the top is 0, and the limit of the bottom is 0, then we find that that limit that you're taking actually equals, it's the same exact thing as taking the limit of the derivative of the top and the derivative of the bottom. If the limit exists or is infinity, then you're finished after you do that. If it comes out 0 over 0 or infinity over infinity again, you just do L'Hopital's rule again. Okay, so we'll do some examples which will make sense. Now, some things that are real important, because this is one of those things where AP is kind of drawing a line in the sand and it's super important to them. So you're going to lose points on the AP test if we don't do it a certain way. So we will definitely write things out a very, very specific way. And then also, in order to use L'Hopital's rule, we have to have conditions that are met, okay? And so we can't have what we call oscillating functions, can't be part of it. So when we do this, the limit has to go to 0 or go to infinity. It can't be oscillating, like sine x, which would just be something that just is oscillating a bunch of values as you go to infinity. So we can't have that. We have to have the limit on the top and bottom each or either 0, both, or infinity. And then if the limit, when you do the limit, as you approach infinity, as x approaches c, if you get infinity, then the limit's just undefined. Like there's not an answer to that. Now, this is the part that's super, super, super important. So like triple, quadruple star this, because it's so easy. And when you do your homework, practice everything the right way. Okay, so make sure you practice everything this way. You need to show that the limit of the top is 0, infinity, or minus infinity, explicitly the bottom, which means you over to the side, you show each one separately. Then you can say by L'Hopital's rule and then do this and so on. So follow what I do in this video carefully. It's super easy, but you have to write it correctly or you will get no points on the test, and that would be terrible because it's not hard. So first thing we always do with every limit is we simply plug in. Well, it's super easy to see that the bottom is going to be 0. So what I'm going to do is over here to the side. I like to do it to the side. You can do it underneath, but I just go to the side and I'm going to say, okay, let's see what this limit is, the top. So I'm going to do the limit of the top. Well, I plug in 5 and I'm going to get 2 times 25, that's 50, minus 45 minus 5, which is 0. So then I'm going to go ahead and write the limit as x approaches 5 of x minus 5, which is the bottom, is also 0. So now you will say, by L'Hopital's rule, that original limit. So I like to rewrite it. You don't have to. It depends on how the problem is. You could just say equals because you're doing the limit, but I like to go ahead and say I'm doing that. It equals the limit as x approaches 5 of 4x minus 9 over 1. So you just do the derivative of the top and do the derivative of the bottom. It's not the quotient rule. It's just literally the derivative of each. Well, once I'm at the point, now I can just plug in 5 and I get the answer, which would be 11. And so I would just stop. Like I don't have to do anything else. If I were to get 0 over 0 again, I would just do it again. Okay? So that's how we're going to write it out. Okay, next example. So previously, to do this example, we would have had to do the whole rationalize the numerator and all that mess, which is why we didn't spend a lot of time on it, because I knew we would get to the point where it would be easier. So I'm going to quickly look, realize the bottom is 0. I'm going to plug -5 into the top. That's going to be 3 minus 3, it's 0. So I'm going to go over here and I'm going to say limit as x approaches -5 of just the numerator, 4 minus x, square root of 4 minus x minus 3 equals 0. Now make sure you're checking it. Don't just write that every time you do limits, because sometimes we just get the answer. We just plug in and we get an answer and we're done. But these happen to both be ones that equal 0. So I'll show you what I would do here is I would just say by L'Hopital's rule, and you do have to say that equals. So the limit is written, and now I'm saying that equals. It's the same thing as the limit as x approaches -5 of. I have to do the derivative of the top over the derivative of the bottom. Well, remember we have scratch work, so if you need some help doing the derivative, then over here in your scratch area, just do that derivative. So you're going to have 4 minus x to the 1/2 minus 3, and that's what you want to do the derivative of. So rewriting it can be helpful. So the derivative d dx of that, okay, is going to be 1/2 of 4 minus x to the -1/2 times -1, and then the derivative of -3 is 0. And then the derivative on the bottom is 1. So I can actually just write that I got -1/2 4 minus x to the -1/2 by L'Hopital's rule. If you want, put it over 1. That just shows you did derivative of top and bottom. And then I can plug in, well, now I'm going to get a number. I'm not going to get 0 over 0 certainly, because I don't have a top and a bottom that are functions anymore, that are functions that have x's in them. So I plug in -5. 4 minus -5 is 9. 9 to the 1/2. Again, scratch area if you can't think about it. 9 to the negative 1/2 means 1 over 9 to the 1/2, which is 1 over the square root of 9, which is a third, times negative 1/2. So this is negative 1/6. And I'm finished. There's my limit. All right. So next one, we may have to do sometimes L'Hopital's rule more than once. So I plug in minus infinity. Well, clearly the top is infinity. E to the minus infinity is e to the infinity, so that's infinity. So I'm going to go ahead and write that, though, because I have to show that. So the limit as x goes to minus infinity of x squared is going to be infinity. The limit as x goes to minus infinity of e to the minus x, also infinity. So now I got infinity over infinity. So then I would say by L'Hopital's rule, I would do the limit as x approaches minus infinity of derivative of the top over derivative of the bottom. Derivative of e to the something is just to rewrite the whole function times the derivative of the inside, because the inside was not plain x. Derivative of the top. Well, now if I put in minus infinity, I'm going to get minus infinity on the top, and I'm going to get minus infinity on the bottom. So I'm going to have to write that again. So I'm going to also say limit as x goes to minus infinity of 2x is going to be minus infinity, because 2 times minus infinity is minus infinity. And on the bottom I have minus e to the minus x. Well, you plug minus infinity for the exponent, you'll have e to the minus infinity. So that's e to the infinity, which is infinity times a negative infinity. So I also did that again. So now I'm going to say by L'Hopital's rule, I'm going to say this equals the limit as x goes to minus infinity. Now, derivative of the top is 2. Derivative of the bottom is just e to the minus x, because the negatives will cancel, because I'll get another negative when I do that. Now, I do not get an indeterminate form anymore because the top is a 2. So now I just have to think about what I have. So the top is a 2. The bottom is e to the minus infinity. Minus a minus infinity is infinity. So it's e to the infinity. 2 over really big, that's 0. Because when the bottom is really big and the top is smaller or a constant, then that's it. Okay, so let's do this one. So here we're going to plug in, again, we're going to plug in negative 2. Now, I'm actually not going to do this one, so we're going to kind of skip this one, but I'm just going to say if you want practice with it, you're just going to have to keep doing L'Hopital's rule a couple of times, because you're going to keep getting an indeterminate form. But I do want to caution you to always check and verify that you are getting indeterminate, because at some point you'll just get a number over a number and it's not indeterminate. So we got to be careful about that. But I don't want to take time to do that, and we're not going to do this one. So we're going to go to example 6. So here again, anytime you see a limit, the first thing you do is try to plug in. So I'm going to plug in 1. So that's going to be ln of 1, which is 0. Minus 1, that's negative 1 plus 1, that's 0. And then I have e to the first minus e, which is 0. So again, over here to the side, right, limit as x goes to 1 of ln of x minus x plus 1, and my answer is 0. We just did it in our heads or sketched it out somewhere. So I'm just showing that what I do is get a 0 over a 0. So then I will write by L'Hopital's rule. Again, I don't use the s at the front, so I'm sure you can all appreciate that since it's less writing. Okay, but I do need to say it's by L'Hopital's rule. It equals the limit of, and its derivative of the top, so that's 1 over x minus 1, that's the derivative of the top, over the derivative of the bottom, which is e to the x. Because e is a constant, so that derivative will be 0. So now I need to check again and see if what I get. So I'm going to plug 1 in. So I get 1 minus 1, which is 0, but the bottom is not 0. It's e to the first. So be cautious there. I do not get 0 over 0. I actually get 0 over e, which equals 0. That is not indeterminate. 0 over a number, 0. Okay, so here's an example of a time on example 7 where I could use L'Hopital's rule. However, we've already learned how to do this, and I would not use L'Hopital's rule here. You get infinity over infinity, but this is hopefully you're all saying in your head, this is a rational function. And for rational functions, when I'm doing a limit as I go to infinity, all I'm going to do is look at the highest powers, and I'm going to reduce that, and that's going to reduce to 3/4, and I'm done, because it's 9 over 12. Because the powers are the same. So don't use L'Hopital's rule if you don't have to. Because I don't want to have to do that. I'd have to do it twice, and it's not necessary. Okay? All right, example 8. So on example 8, again, I can also use L'Hopital's rule. But we're also going to start to learn some things, because you don't actually have to show steps when you do limits other than L'Hopital's rule. I really don't have to show, I just need to do the limit when it's a clear limit that I can figure out. I'm going to infinity, okay? The top is a power function. I have 4x squared as the biggest thing up there. It's a polynomial. The bottom is an exponential plus another increasing function. Ln increases ridiculously slow, but it is increasing. So essentially, again, I'm going to look at the highest things that are making a difference, because those are the things that are going to actually affect the end behavior, which is what we want when we're going to infinity. Well, you have an x squared over an exponential. If the bottom is way bigger than the top, this answer is 0. So I do not have to go through all of that trouble, because essentially what I have is I have some big number. Essentially, I'm going to infinity. I have some big number over a really, really big number. Okay, so the bottom is just growing so much faster than the top that the limit is going to end up being 0. Okay, so whenever possible, we definitely want to just answer the question. Okay, so we want to do that for that situation. Okay, example 9 is using a table to answer this. This is actually when it sometimes comes up on the AP test on a free response portion. So here we have a table of values. They tell you the function is twice differentiable, which is important. It means the second derivative exists everywhere. Use the table to find the limit if it exists and justify your answer. So, first step, every problem, even on this homework, L'Hopital's rule may not be applied on this homework on every problem, so don't fall for that. Every single time, you always plug in first and look at the limit. It's only if it's 0 over 0 or an infinity over an infinity that you would decide to do L'Hopital's rule. So really important to remember that. So I would just plug in right here. So I'm going to kind of do some scratch work and say, okay, if I plug in -2, I'm going to do f of -6 plus 2, which is f of -4. Well, they give me this in the table. F of -4 is 0. Okay, right here. F of -4 is 0. On the bottom, I plug in -2, I'm going to get 4 minus 4, which is also 0. So now I'm going to have to show that. Okay, so I'm going to write limit as x approaches -2 of f of 3x plus 2 equals 0. Limit as x approaches -2 of x squared minus 4 equals 0. So that means I can use L'Hopital's rule here. So by L'Hopital's rule, okay, this equals the limit as x approaches -2. Again, I have to evaluate first and verify that they do in fact equal 0 over 0. or an infinity over infinity. Don't just assume, okay, actually check it. So now L'Hopital's rule says take the derivative of the top. So the derivative of the top would be the derivative of 3x plus 2 times the derivative of the inside, because clearly the inside is not plain x. So that would just be times 3. So I'm just going to stick it in front. And the bottom's derivative is 2x. So clearly I will not get another indeterminate form here because the bottom is -4. So I'm just going to go ahead and plug stuff in. So the top is going to be 3 times f prime of the -6 plus 2, which is -4, over -4, which is going to be 3 times f prime of -4 is 8. So that's going to be 3 times 8 over -4, which is 24 over -4, or you can simplify it different ways, but I get -6. Okay, so that's the proper way to write all of that down, and very common to, that's a common place where you might see L'Hopital's rule on the test. Okay, so we're going to do this example, and then we're going to discuss the last example as a quicker way we can do it. So here's another way they might ask you to do a limit. So they give you a graph. Now this is the graph of g, not the graph of the derivative, so pay attention. Always look, because sometimes they give you the derivatives graph or whatever. This time they did not. They gave me the graph of g. So I'm supposed to find the limit as x goes to 3 of g of x over x minus 3. Well, clearly the bottom is 0, but don't assume L'Hopital's rule yet. Let's make sure the top is 0. So I need to do, the top is going to be g of 3. So this graph is g. The top limit then is actually not 0, it's 2. I actually have a value there. So this limit actually equals, you could even write g of 3 in order to show some work there, over 0. G of 3 is 2, so this is 2 over 0. So the limit as x approaches 3 of g of x over x minus 3 does not exist. Do not put equals does not exist, because that doesn't make sense, but we did get something that does not exist. Okay, and we can't use L'Hopital's rule, so be careful. Don't just assume that it's always 0 over 0. Okay, we're going to skip 11 and we're going to go to number 12. We might do 11 in class, but right now we're going to look at 12. So 12 is another example. We're going to infinity and we're going to look at these two different things instead of doing L'Hopital's rule. Because just imagine for a moment if you did L'Hopital's rule here. The bottom is x to the 99th. That means you're going to have to do L'Hopital's rule, 90 sometimes, right? Because you have to keep doing it, keep doing it, keep doing it, keep doing it. You're never going to get rid of it. The top's going to keep having a 2 to the x in it. So that's where, if again, I want to know and understand what's going on. It doesn't matter that this is x to the 99th. It's still a power function. It's a power. The top is an exponential. Exponentials are always greater than a power function as I go to infinity. Now, not for small values, but we're not looking at small values. We're saying what happens as I go to infinity. So eventually, no matter how big a power function is, an exponential is just so much bigger. So that means the top of this is going to be infinity and the bottom's infinity, but my answer here is does not exist because the top is going to infinity so much faster than the bottom. And you really don't have to show any work here because you certainly aren't doing L'Hopital's rule a million times. But if you feel better on a free response question, you could say, well, an exponential function grows much more rapidly than a power function, so this is going to go to infinity, so this limit does not exist. Or you could even put, actually, we could even put that this equals infinity, but remember, we're looking for the limit exists or not exists. Okay? So we don't always have to do the algebra work for limits. So please take this assignment seriously and really pay attention on these notes, and then we'll do maybe a couple more things in class, and then we'll you'll practice doing this. It's really all about, it's not hard, it's all about how to write it out, okay, so that you practice correctly, so that you don't lose any points when you take the AP test. All right, so that's it for this video.